This is a lesson on modeling in a regression with linear functions in a precalculus course. This could seem like intimidating material, but I actually find regression can be one of the easier things to learn, and interpreting may be the more difficult part. I'm going to start with modeling with linear functions, and this is likely a review for most people. I expect at this point in your math curriculum path, modeling with linear functions is not new. You've used this in word problems before. You've used this form. Now we're emphasizing to use function notation. All right. And the word problems may be getting a little bit more involved. I'm going to remind you right away that words mean things. Okay, look for keywords or phrases, right? Because words mean things. You can look for cues in the problem statement that have mathematical implications, okay? As you're doing this, identify your knowns and unknowns. Identify your unknowns and your knowns in the problem and assign symbols to them. Remember that we have a whole function with symbols in here, right, with letters. So if you can identify anything meaningful from the problem statement, that is a slope or a point or an intercept or anything, an inequality, an equality, anything like that going on, make sure that you're using symbols and you're thinking about the mathematical implications there. And that's because we want to create an algebraic equation. We are in precalculus, all right? We are learning to use algebra to solve. We're going to manipulate equations and inequalities algebraically to solve for numerical values. We're not just guessing numbers. And also, we're not just looking at graphs. We need to be able to do this algebraically. So as you're looking at your symbols, your unknowns, and your knowns, you're trying to get an equation going for each unknown variable. So just a reminder, if you have one unknown, you need one equation. If you have two unknowns, you need two equations. If you have three unknowns, you have three equations. It depends on the problem. I want you to use algebra to solve, and this involves strategies for how to find equations for lines or solve lines, right? We can write an equation of a line if we're given the slope and the intercept. If we know m and b, we know the equation of a line. If we're given an intercept and a point, if we're given an intercept and a point, we'll know the y-intercept. I put intercept here, but this is the y-intercept. If we're given the b value, then we have that in the equation. And if we have another point, we'd be able to find the slope. That wouldn't be hard to do. And we can also find a slope with 2 points, right? y2 minus y1 over x2 minus x1. So that means we need an x1, y1, and an x2, y2 from the problem statement. We're looking for a single point and another single point, and then we can write an equation of a line from there. I'm going to remind you again, use function notation where appropriate, and always, always, always verify your algebraic solution with a graph, okay? Let's take our first look at cricket chirps. We're going to keep working with the cricket chirps problem, but we're just going to do this one. It's a word problem. Entomologists are biological scientists who study insects. Entomologists studying tree crickets have found that they chirp at different rates depending on the temperature. The number of chirps per minute C that the tree cricket makes is linearly dependent. Okay, so that right away tells me that I'm going to be using y equals mx plus b. Of course, I need to use function notation. But what I'm going to notice here is that they've already assigned symbols. So when you do this, you need to use the symbols assigned, not x and y. So it says that the crickets is linearly dependent on the temperature. So what I'm going to note is the number of chirps is a function of temperature, and so I'm going to have a slope times temperature plus some initial value. So that's going to be my general linear model that I'm going to use to solve this problem. It says the crickets do not chirp at all below 34 degrees, and at 62 degrees they chirp about 126 times per minute. This is giving me 2 points. I have 2 points on a line. All right, so I'll notice that I have the point when the input is 34, then the output is 0. That's not 0, 34. That's not an intercept value. Make sure you're interpreting your points correctly. So there's that first point, 34, 0. And then the other one is when the temperature is 62, I'm going to have a number of chirps of 26. Okay, so that is going to be our 2 points. And I'm going to use the 2 points to find a function and fill in the m and the b values for that linear function. Express the number of chirps c as a function of the temperature t. Okay, so I took a second and I graphed these 2 points. There's those 2 points. What we're doing is we're just going to find the equation of the line that connects those 2 points. Okay, whatever the equation of that line is. And what I'm going to note is that the y-intercept is actually way down here somewhere. I need to calculate it. I can't eyeball it on a graph. All right. So the first thing we want to do is find the slope. Remember, we can always find the slope if we have 2 points. So I'm going to take y2 minus y1 over x2 minus x1. What do I get? 126 over... Oh no, 8, what is that, 28. And that simplifies magically. I don't know if you can do math in your head. I'm looking at the solution. I didn't do the math in my head on that one. That's 4.5. All right, so that's the slope of that line. And so I have the slope of the line. I know that c of t is going to be 4.5t plus some y-intercept. I need to solve for that y-intercept. The easiest way for me to solve for that y-intercept is just to plug in a point in here. So I'm going to say 0 equals 4.5 times 34 plus b. Well, if you can do 4.5 times 34 in your head and move it also to the other side, we're going to have a negative sign in here. You're going to know that b, that y-intercept, is negative 153. So our answer for part A is c of t equals 4.5 times t minus 153. That's going to be your answer for that first part. Part B asks, how many chirps per minute will the cricket make at 76 degrees? Well, I have a temperature, so it seems all they want me to do is put 76 into the equation that I just found. So I'm going to take 4.5 and multiply by 76 and then subtract 153. And when we do this, you can do that math in your head. You'll get 189. And this will be chirps per minute. Okay. I can double check where that is on the graph. I can make sure that my lines fit. So there's that line, that green line is the function. And I can see that when I have 72, that's somewhere in here, right? When I have 72, I'm going to have, oh, it goes off the graph. I'm going to have 189 chirps. And then there's that y-intercept, negative 153 that I solved for. So when you're solving, look at your graph. Make sure your graph, always include your graph with your written work and for when you submit for me. And look at that graph and make sure that your points are on the line, that everything makes sense. You can double check that value for 76 and make sure that it lines up with 189 and you did all your math correctly. So I'm going to leave you to practice on linear modeling with word problems, with more problems in your practice problems in your work. We're going to move forward to linear regression with linear models. So what I am introducing to you here with regression, and if you've had statistics before, you may have seen regression before. But I am taking it upon me to teach you what I need you to know about regression with modeling this quarter. The first model that we're going to use for regression is linear. We're going to move to quadratic. We're going to move to more of them, right? But we're starting with linear models. So I'm going to lay a foundation for regression with a linear model as an example. And when you're doing regression, when you're looking at data for any intents and purposes, always, always, always graph the data and look at it. What we're going to notice about, again, we're going to have cricket chirps versus temperature. Notice that oh, I don't like this graph. Do you all see why I don't? This label is incorrect. When you label this, you should put the y first, temperature versus chirps. All right. So, and you can see that up here. The chirps they have as the input variable. And if you know the number of chirps, that means you can predict what the temperature is. If you listen to a cricket chirping and then you put it into this function, you can say, oh, now I know the temperature. Okay, so temperature versus chirps. And you can see when you look at the data given, so here's the little data table, and we've done something like this similar in class. There's a line, it looks kind of linear. There's some variation going on, right? But there's a general linear trend, right? So what we're looking at immediately, we're going to decide whether this is a linear or nonlinear trend. We're going to look at nonlinear trends as we move forward, but what we're noticing about this one is it's roughly linear. It's not perfect, but that's all right. That's what the regression will take care of. So if it's linear, we're going to assume the model of the form y equals mx plus b. Or in this situation, we're going to have temperature goes as, that's what this means, goes as m times the number of chirps plus some initial value. All right. You can formalize this more as you pursue statistics. There's a lot more going on, but that for all intents and purposes in this class, that's what you need to know, is that we're going to let y goes as mx plus b. So we need to figure out the m and we need to figure out the b. Whether we're working with chirps or whatever variables we're working with, we need to figure out the m and the b. So the first way to do this, there's two methods overall. And this was probably used more back in the day. We are readily available technology to do all our analyses. But back in the day, if you just wanted to get like a rough idea, all right, you would just roughly sketch a line. You just take a ruler and draw a nice line through the middle of that data. All right, and this is what we're going to call the line of best fit. And best fit here has a pretty, I want to say sharp definition, the best fit. When you work on problems, there's a little bit of variation that the computer will accept when you draw your line of best fit. But you want to do the best you can, right? It's called the line of best fit. And what we're looking at here is the points above the line are as much above the line as the points that are below the line are below the line. So when I look at this data, I have this point above the line, I have this point below the line, I have this point below the line, I have a bunch of these below the line here, I have a couple of them on the line. I don't agree necessarily that this is the line of best fit. I think I would have made it go a little bit lower through the data and have a steeper slope. But I do believe what they did here was they just picked 2 points. All right. 0, 30. When they drew this line, they took the edge here, 0, 30. So really, maybe it was a point of convenience, right? I would have drawn it steeper and maybe gone like 25 or something, right? But they picked 0.030, and on the other edge, so they didn't use the actual data. They used the line extended to the edge outside the data, and they just picked 2 nice points. We can see that there's 50, 90 on this other edge of the data. And using the same strategy that I used in the linear model problem with the cricket chirps, you can use that to find a slope, and you can use that to find the y value. Of course, the y value is easy in this situation. We have the y-intercept, and you can use the values to find the slope. And that's how you do method 1. The temperature is a function of the chirps is going to be that value, that equation. That's it. You could estimate what's going on if you wanted to find, like, if you hear 10 chirps, is it about 40 degrees? You could predict what the temperature is. That was the whole point, right? So that's the first method. Like I mentioned, it's not as precise. We're just eyeballing it. And even with this red line on here, I didn't agree that it was the best fit. It would seem like it was a convenient fit, but not a best fit. The bestest fit, the most best fit is going to be from technology. The technology is going to do what it does in order to find the best regression line that makes sure that data is just as much above the line as below the line. So I kept the same graph as before. So this is the best fit line. I'll put line of best fit. That's that red one there. But that is not the bestest line. What we're going to do is use statistical techniques for fitting a line to the data that mathematically minimize, so we're doing a minimization, the differences between the line and the data values. So when the computer does some calculations, and I just put broadly here, these are details that involve statistics regarding calculation of residuals, or what's called error, that are beyond the scope of the class. You don't need to know how least squared regression works at all. That is not the point of this class. What I need you to know is how to program in Desmos or Excel a regression and get the output. Okay, so we're going to just work on the output of it, not the how it works. We'll leave that as a black box for now. We're going to look at the output of it. So we're going to input into the data analysis program and fit a linear regression model to the data. Okay, so here's the data. It's the same data, okay? And you can see how the equation of the line that was produced by this computer program by a least squared proper regression line, it did all of the calculations for us. It gave us 1.143 times the number of chirps, and I'm correcting this to a capital C rather than a little c, plus 30.281, which is different than the eyeball. Remember, if you remember the value for that, that was 1.2c plus 30. And so you can see that this line of best fit and the accurate line from the least squared regression output, they're pretty close to one another. They're not exactly. And you can see how the line of best fit got us to like a general, it's an okay equation, but the one that the computer outputs from a linear regression is going to be the most accurate. When you get output from a computer, they will use the variables x and y, but remember in this situation, you want to clearly designate your input and output variables. So in this situation, our output is the temperature, our input is the number of chirps, C. I guess it's a little c on this one. Maybe that's why I had a little c there. We can predict if I hear 10 chirps, what's the temperature? I could predict if I hear 30 chirps, what's the temperature, right? What's going on there? So we are going to have a quick discussion about the difference between interpolation and extrapolation from a model. We have our model, right? What is it? 1.143 C plus 30.281 is the temperature as a function of chirps, right? And interpolation occurs within the domain and range of the provided data. So any value in here, so any temperature from whatever this is to whatever this is going to be interpolation. Extrapolation occurs outside the domain and range of the original data. Okay, so out here is going to be extrapolation, and out here is going to be extrapolation. Okay, that's riskier. We can see for within the data, that data is pretty linear, but what the assumption we're making is that data outside the original data will also follow the trend that happens inside the data. And that can be risky. It could be that the function goes down like this. It could be that the function goes up like this. It could be that it drops to nothing. We don't know for certain. We're taking this risk when we extrapolate that this assumption that whatever is happening inside the data is going to be the same thing that's happening outside the data. It's a risky prediction. So my quick quiz here, would predicting the temperature when the crickets are chirping 30 times in 15 seconds be interpolation or extrapolation? We can see looking at the graph, there's the 30. I'd mentioned this earlier. It's within our data, so it's interpolation. How about this one? Would predicting the number of chirps crickets will make at 40 degrees be interpolation or extrapolation? All right, watch your axes here. We have a temperature of 40 degrees, so that's over here. Everybody see 40 degrees over here? So this is 40 degrees. I'm going to go over and see that this is outside my data, so this is extrapolation, whereas inside is interpolation. Okay, so mostly overall on that slide, I wanted to just highlight the risk of extrapolation. You don't want to, and I have this here, the model breaks down. It may be that the model outside the data isn't accurate for what's inside the data. Another thing that I wanted to talk about in regard to regression is how well the model fits the data. And again, we're looking at this in regard to a linear regression, but this idea is true if I have a quadratic, if I have a power function, if I have an inverse function. Any of those is going to have data that may be well behaved along our function, or there may be a bunch of variation, and we're interested in how a measure of how much variation in the data is accounted for by our model. So in this situation, we have a linear model. Again, it could be any type of model, any of our two-kit models. And we call that the correlation coefficient. And we denote it with an R, especially if we just have two variables. If we have X and Y, we're going to have just a little r. Big R is if we have like an X1 and X2 and X3 and it results in some output variable. We call that multivariate regression, all right? We're not going to do this class, but I wanted to clarify as we're stepping into correlation coefficient what the difference is, because we see in class an R squared actually when we generate our regressions. So important characteristics of R or big R, all right? It has a range between -1 and 1, okay? If it is positive, so if it's 0 to 1, if R is greater than 0, if it's 0 to 1, that suggests a positive or increasing relationship, which is what you see over here. We have a 1, we have a 0.8. Overall, we see the slope on that line is positive. If there's a negative sign, we know that about negative slope, it goes the other direction. The other thing I wanted to mention here, the closer the value is to 0, the more scattered the data. You can see that this example I give here. 1 is a nearly perfect fit. It is actually, if you get 1, it is an absolutely perfect fit. That will never happen in the real world. You'd have to get like made up data to get 1. 0.8, you can see 0.8 over here. There's some variation around that line. There's some points above, there's some points below, but overall they're kind of like bunched in that. You can see that there's a linear fit. It's not nonlinear, right? So the closer the value is to 1 or -1, the less scattered the data is. The more it's closer to 0, the more scattered the data is. When we generate these regressions in our technology, whether we're using Desmos or Excel or what have you, it will output an R squared value. It will not output R, it will output the R squared value. And how I interpret this, and this is true in the statistics field, we call this a coefficient of determination, and I actually like this value more than the R value. I like an R squared value. What it tells me is the fraction or percentage of variation accounted for in the model. So when I look at 1, 100% of the variation of this data is accounted for by the line. Here, only 80% of the variation is accounted for by the line. There's some other things going on. This other 20% of variation is caused by things outside of our control and not accounted for by just a linear model. I'll look at an example here in a little bit with age and height. And age and height seem to be pretty well correlated, but nutrition makes a difference. So maybe that nutrition is in that extra 20% that's not accounted for in age, right? So our models don't always perfectly fit the data, and it's important to know how well that model fits the data. Let's look at a little bit of example. So I have you, the first thing I said when we walked into regression is, modeling, right, is to make sure that you're drawing your graph. Always, always, always graph your data. Always graph your data. And what we're looking for, and this is where I'm going, is the R squared or R squared, right? R squared for linear models on graphs. So I showed you these two on the previous slide, right? 1 and 0.8. You can see that 0.4 has much more scattered data. There's 0. There is no correlation there. It is just as wide and just as tall in both directions. There's no correlation. Any line through there is going to be just as good of a predictor. There's no correlation there to any line. All right, you can see over on this side where I had said that the correlation is going to be negative. We're going to have a negative slope on that line of best fit. All of these have a fit of 100%. They're all perfectly along that line, but you can see that just because you have a correlation of 1 or negative 1, that doesn't mean that the slope is 1 or negative 1. That correlation is related to how well that data fits on the line, not the slope of the line. This last line down here, the last row down here, I really appreciate that they have this example, because you can have data all over the place and it may be exhibiting an interesting pattern that's not linear, right? That's what this output says, is I'm going to put this and try to fit a linear function, and there's no linear function that fits this. There's no linear function that fits this. There's no linear function that fits this. That looks like a line, but there's no linear function, right? It has to be, there's no mx plus b that will fit this. Actually, you're just going to have y equals some number, some value. That's not a linear function. That's a constant function, okay? What I'm going to notice here is that a line fits through here very nicely, but there's no correlation. I think a line could fit in any direction. There's lots of symmetry in here, and a line could fit in any direction. There's no preferred line through that data. I might even say that this one would be best modeled by a parabola rather than a line, right? A line through here might look like that, but a parabola might be something that better represents the shape of that data. Obviously, a circle is going to be the best function there, and a circle isn't even a function because it doesn't follow the one-to-one, the vertical line test, right? This one down here has some interesting stuff. If I was a researcher working with this data, I'd be very interested what was going on there. But there's no line that fits perfectly through that data. This line or this line or this line, they can all be a perfectly good line for that data. So we're going to say that there's no line that actually fits that. There's no linear correlation. Let's do an example and just do some basic linear regression. This is the one where I was referring to, I'm pretty sure it just says A and H on here, but I think this is age and this is height. And this may be for first graders through sixth graders. I don't know what it is. So I'm going to graph age and height, right? So when I graph this, I'm going to have height on the vertical axis and age as the input variable on the horizontal axis. And when I do that, I'm also going to do the regression. So this is a Desmos example. When you do this in Desmos, this is the graphs that I generated in Desmos when I was doing this example. Let me move this over here out of the way. I'll move that over here out of the way, and we have our output. So you can see when I entered this data into Desmos, I use two columns. The first column, x, is always the input variable. Make sure you're putting the input variable in the x and the output in the y. So this was age and this was height. And you can see I entered the values downward, okay? And I did that by selecting the plus and choosing the table function in there, okay? I also added another line in here, so that's one. Two, I added my model. I'm going to note my variables up here. My variables, my input variable is x1 is labeled at the top of that table, and the output is y1, so that's what I'm going to use when I tell the model. Okay, I know that Desmos has some options and you can choose a linear regression, but I want you to get in the habit of writing out your model. So, because we're going to change it. We're going to change it. Maybe a power, it may be an inverse. What I want you to show me is that you're really aware of what your model is. You're not just letting the program do some magical calculations for you, but you know exactly what's going on. So we can see the regression parameters, that m value, we can see is 29.82. And we can see the intercept value is 641.6. All right. It says use the indicated variables and produce, I think it says a function, round to 3 decimal places as needed. So when I write the equation for this regression line, I'm going to use the variables given in the problem. So I'm going to say h of a equals 29.829, right, rounding to 3 decimals, times age, plus 641.6. There's no rounding I need to do there. So this would be the result of our linear regression. Notice I do not have x and y in here. I have h and a, okay? The other thing I wanted to highlight on this is our output. Notice they give me an r squared, which is nice. It's telling me 94.52% of the variation in this data. So any place where you see this a little bit off the line, they're really close here. It's really close on this line. 94.52% of the variation in the data is accounted for by that linear model. That linear model goes a long way into relating those data. I just take the square root and that will give me the R, the correlation coefficient. Remember, this is the coefficient of determination, and this is the correlation coefficient. So when you see correlation coefficient, this is what they're looking for. I'm going to note that it's positive, and that makes sense because I have a positive line. And again, note that this correlation coefficient is not the slope of the line. The slope of the line is given up here. It's almost 30, right? The correlation coefficient says how well does that data fit that line. So that's a basic linear regression in Desmos. That's how you do that in Desmos. I want to show you another example. We're just doing examples here. Use the regression model to predict a value. The following data is the first and second test scores for 8 students in a class. I'm going to tell you, based on what research I've done in education, the minimum value for students in a class, to have it be like statistically significant, would be like 30, 35, 40 students. That's the minimum number where you're like, okay, I have enough number of people involved that I can rely on it. And that's a whole other study in statistics. But 8 students, it'll give a trend, but I wouldn't be confident about it. It says plot the points, so they just give the points here, and what I did was I showed the solution. You're gonna, on this graph, you're gonna go through and you're gonna put these points on this graph. You're gonna, each one of these points, you're gonna plot on that graph. And then it says use the line, plot the points on the grid and then sketch a line that best fits the data. So you're gonna kind of eyeball it. You're gonna choose a line and you're gonna go from one point to another across the graph and have that data. My tip is to have just as many points a distance above and just as many points a distance below, so that it kind of balances out, right? It's going to accept a little bit of a range, so do the best you can, but we're having just as much above as it is below. And so that's that line there that the computer is looking for on this problem. Okay, that's the answer. I went through and I plugged this into Desmos. You can see that's the output from Desmos. I'm going to enlarge this on here so you can see the output here. And there's the equation of the line. I put in all of the first test scores, and then I put in all the second test scores. I told it my model, y goes as mx plus b, and it output for me. They have the m value on this line. So I'm going to do test 2 as a function of test 1 is going to be 1.25114 test 1 minus 18.21347. That's the equation, the regression equation that Desmos put out for me. And the r squared, you can see down here, is also 94.5%. 94.5% of the variation in the data is accounted for by that linear model. They tell us the correlation coefficient is 0.9721. So it's pretty close to 1. It's a very good fit overall, and it's positive, which we expect. We have a positive slope. The one thing that I really want to make note of while I'm here is that intercept value really doesn't have any meaning. Negative 18 point something. It's saying that if you have an initial test score of 0, your second test score is going to be negative 18.2, which makes no sense. This is outside the realistic bounds, right? The lowest test score you can have is 0 for the initial and 0 for the other one, right? You can't have anything in this region be within a practical domain or a practical range. This is an initial value that really doesn't have a real meaning, but it's an important part of the equation. We can't just leave it out. Another thing I'm going to note is that the slope is 1.25. I'm going to note that you're going to have an increase in exam score. I hope that's true as the quarter semester goes along, that your second test score is better than your first test score. It could be worse. It depends on the class, right? But that's how I interpret that, is that your second test score is going to be greater than your first test score. Let's also look at the second question. It says, use the line above to predict the value of the second test score if your first test score is 73. So I think you could just eyeball this. I think if you do your graph, you can just eyeball it. But what I'm going to note is that you can take that value 73 and plug it in here. Just plug in 73. Just plug it in and do the calculation. When you do the calculation, you get 73.11986. I think it asks for a whole number. So I would say 73. If you score 73 on the first one, you're going to score a 73 on the second one. I don't think that's very foreboding, but that is true. So we're going to use the equation that we got before in order to make a prediction. If I ask you, is this an extrapolation or an interpolation? What do you think for 73? Is that an extrapolation or an interpolation? I'm having trouble saying that word, interpolation. It's within our data, isn't it? Yeah, 73 is definitely within our data, so it's going to be an interpolation. We're going to have some confidence if a student gets a 73 on the first exam score. Pretty confidently, we know they're going to get a 73 on the second exam because it's within our original data. This last problem here, I want to show you because it's how to do a regression in Excel. You may have a teacher, me, who wants you to know how to do a regression in Excel. Excel is a very fine way to manage data as long as you have the desktop version, not the browser version of it. All right, so I'm going to do the Excel version. This is based on the data shown below. Calculate the correlation coefficient. And I actually have it down here. You can see the answer down here. Calculate the correlation coefficient rounded to 3 decimal places. So we're going to go through the process of getting a regression equation, but in Excel rather than Desmos. So you can have this in your pocket as a strategy and refer this if you need to use Excel. So of course, what I did was I entered the data as columns in Excel. And so that looked like this. You can see the purple and the blue. I just chose 2 columns in Excel, the purple and the blue, 2 through 8 on one side, and then I entered the values on the other. And what I did was I highlighted that data. What I'm going to make note here is you do not need any headers on this. Excel does not care if you have headers on it, and even better, it works way better without headers. Excel tends to freak out if you choose any letters in your data, so I don't put any letters anywhere in my spreadsheet to begin with, so Excel doesn't get confused, all right? So I selected that data overall. When you have it in this order, it's always going to assume that the first column you choose is the input and the second column you choose is the output. It's going to assume that. So when I highlight that, I'm going to go up to Insert on my menu, and I'm going to go over to the scatter plot, and I'm going to choose the first option here, just a basic XY scatter. I make fun of people who use like other options in here. I call it the kindergarten connect the dot version. Social sciences use this, and I think they like connecting the dots. Scientists don't do this. All right, we're just going to look, and you've seen that in all the data before. We're not connecting any dots. What we're doing is we're putting the data on a plot, and we're inspecting the nature of that data. And any lines in there aren't going to give us any information. What we're seeing when we plot this data, all right, so that's that data plotted down there, is it's roughly linear. I'm okay with that. It's roughly linear. Overall, I have a little bit of thing going on, and then it does this. It's a little curvy, but overall, I could see fitting a line through that data, okay? So that's your first step, is enter your data, and then insert a plain old scatter plot and just get that scatter plot going. I'm going to get rid of some of this in here so that I can put this next screenshot on here. The next screenshot I have on here is, here's my data, and I have the plot. What I'm going to do is go to my plot, and I'm going to choose, in order to add a trend line, I'm going to choose the trend line function over here. I'm going to choose this arrow, and I'm not going to choose linear right away. I'm going to choose the more options down at the bottom. Once I choose the more options down at the bottom, I'm going to get this over to the side. And admittedly, when I produce this, I know this from class working with students that there are different versions, right? Different programs. You may be on a Mac, you may be in spreadsheets, however you're using this. I know Excel isn't the same as spreadsheets, but this format trend line may look different for you. And what I need you to select is to make sure it's linear. You can see that we have other options in here: exponential, logarithmic, polynomial, power, blah, blah, blah. All right. So like I said, we're just starting with linear. There's other options down here. We're going to trend line name, automatic, that's fine. Forecast, set, intercept. There's other things in here that you may use at some point, but most important at this point in your learning of doing regression, I want you to display the equation on the chart, and I want you to display the R squared on the chart. All right, I think my layers are coming back to haunt me here, okay? So display equation and display R squared on the chart, and you can see that's what pops up here. That's the equation in X and Y, and you can see the R squared on the chart. It doesn't give an R, it gives an R squared, okay? So that's why it's important for you to go into formatted trend line, because that's how you get that equation and the r squared on your chart. What I like to do, and I'm creating another layer here, I like to take that just text box, I just click on it and I make it bold, and then I make it bigger. I make the the font bigger. I also in here make my graph prettier. A lot of teachers, biochem, they get really upset if you don't do this. Make sure you put a title on the top. I wasn't given variables. I don't know what they are. It's y versus x, and I put a y on this side and an x on this side. Just make your plot so that it's apparent what your variables are on your horizontal and vertical axes, and you label your chart. And then I want to see this clearly on your chart as well. All right. So when we're looking at this, let's answer the question at once. What is r? What is the r? Well, I'm going to take the square root of r squared, right? R is the square root of r squared. So I'm going to take the square root of 0.9833, and the square root of that, r is 0.991 and some stuff. So it rounds to 992. So that's how I get the answer to that. And hopefully you're able to parse through, fumble through getting an Excel trend line linear. And we'll do this more in class with more models, quadratic, power, polynomial. We'll do that as we move through the class.